Welcome to the Explainer. When we use AI today, it's so easy to picture it as just this abstract magic, right? Like invisible lines of code floating effortlessly up in the cloud somewhere. But when you actually dive into the architecture of modern AI, you hit a brutally physical reality. It is heavy, it is incredibly hot, and it requires a truly staggering amount of infrastructure. So, today we're exploring the design of AI data centers, and we're going to discover exactly what it physically takes to engineer intelligence at scale. Okay, let's dive into this. If you think about it, every single great transformation in human history has been defined by mastering a new form of power. Fire transformed raw materials into tools. Steam engines transformed human labor. Electricity revolutionized mass production. And now, well, compute is transforming cognition itself. Think about the sheer raw energy density required to turn massive, sprawling datasets into actual usable intelligence. The AI chips powering today's breakthroughs, they aren't just your standard hardware upgrade. They represent a fundamental civilizational shift. The new industrial output of our era isn't steel and it isn't oil. It is literally scalable intelligence. And that brings us to a really foundational concept here. At AI scale, intelligence becomes a thermodynamic event. Let's make that real for a second. If you're just hosting a standard website, the servers emit a pretty predictable, manageable amount of heat. But when you rack up thousands of highly specialized GPUs running complex language model inference, the density of the heat generated is just on an entirely different scale. Every single time you prompt an AI to synthesize a research paper or generate complex code, you're initiating a highly concentrated physical process, one that demands massive power and generates intense thermal energy. AI isn't magic. It is a remarkably resource-intensive physical undertaking. So here's our roadmap for today. First, compute is the new fire. Second, anatomy of the AI factory. Third, the physics of intelligence. Fourth, security at machine speed. And finally, scaling responsibility. All right, let's kick things off with Section 1. Compute is the new fire, a civilizational driver. We are moving way, way beyond the traditional idea of a data center here. It's no longer just some passive warehouse where you store servers. It has evolved into what we call an AI factory. And this reframing is crucial because it forces us to see the facility as a new kind of industrial organism. Seriously, it's a living, breathing system with its very own metabolism. But what does it actually mean for a building to have a metabolism? Well, it means the facility is actively synthesizing raw power, cooling water, and massive fiber optic data streams. It converts those base physical inputs into scalable cognition. It's a continuous, highly active process of digesting energy and data to literally produce intelligence. Moving into Section 2, Anatomy of the AI Factory, a layered organism. So if we're dealing with an industrial organism, we have to understand how its biology works across three distinct layers. First up, you have the physical body. This is the hardware, the immense compute halls, the heavy power systems, and the cooling loops that act like the system's veins. Next, you have the logical metabolism. Just like a human body breaks down food to distribute energy, this layer schedules the tasks, orchestrates really complex workloads, and moves data precisely where it needs to go. And finally, sitting right on top is the autonomic control plane. Think of this as the brain's regulatory system, governing the overall intent and enforcing security. Now, the reason separating these layers matters so much is all about resilience. For instance, the autonomic control plane absolutely needs to be completely isolated from the logical metabolism. Why? Because if the system gets hit with a massive spike in workloads and the metabolism gets overwhelmed, you really don't want your security and governance crashing right along with it. And those biological layers manifest into 6 vital design pillars: compute, network, power, sustainability, security, and governance. The biggest takeaway here is that you simply cannot design these in silos anymore. Let's look at how intertwined they really are. Take liquid cooling, for example. That's typically seen as a sustainability metric, right? But moving to liquid cooling allows you to place the AI chips much closer together, which directly increases your compute density. Because the chips are physically closer, your cable links are shorter, and shorter cables, that directly improves your network latency. It's all connected. Crafting this ecosystem requires understanding that the moment you pull one lever, you instantly move the other 5. This brings us to Section 3, the physics of intelligence, density, and geography. The contrast between traditional infrastructure and these new AI factories is absolutely staggering. Traditional data centers operate in megawatts. They rely mostly on standard air conditioning to cool the servers, and their design is largely focused on network speed. But an AI factory, it operates in gigawatts. To put that into perspective, a single AI factory might require the power equivalent of a medium-sized city. The heat generated by these massive GPU clusters is so incredibly dense that blowing cold air on them just fails entirely. You literally have to run liquid directly to the chips to keep them from melting. We've gone from managing a standard utility footprint to managing a major thermodynamic event. And because of that incredible leap in scale, compute genuinely becomes geography. It used to be that you could put a data center pretty much anywhere you could buy a big enough plot of commercial real estate, but not anymore. Site selection today is rigidly dictated by unforgiving physical limits. You literally have to look at a map and ask, where exactly does a massive power grid, the necessary water table, and a heavy fiber optic backbone all intersect perfectly? You aren't just buying land anymore, you are buying into the local physics of a specific region. Naturally, those physical realities introduce some pretty severe strategic constraints. Energy is the raw material here, meaning high-capacity grid access and localized microgrids are absolutely critical. And because of that intense heat we talked about, liquid and immersion cooling are mandatory. But here's where it gets really important for the communities surrounding these factories: water usage. Facilities have to aim for water-neutral operations. That means using closed loops and intelligent stewardship rather than just draining local reservoirs. And then there's circularity. Think about the massive waste heat generated by the AI answering your everyday prompts. In an advanced circular design, that heat is captured and reused. It could literally be piped out to heat a municipal greenhouse or a block of local office buildings, like they do in some Nordic countries. The organism has to sustain itself without destroying the surrounding environment. All right, Section 4, Security at Machine Speed, Immune Systems. Now, what's really interesting about this slide is how it forces us to rethink protection entirely. Seriously, how on earth do you secure an entity that thinks and adapts this quickly? Well, the short answer is that old, static security checklists simply fail. Imagine an AI infrastructure that is constantly training itself, inferring new data patterns, moving petabytes of information, and taking autonomous actions in literal milliseconds. A human sitting at a security console cannot possibly keep up with that volume and velocity. You just can't put a static human speed gate on a completely fluid machine speed system. It doesn't work. Instead, the security must act biologically. It needs an immune system, dynamic protection featuring zero-trust architectures and runtime integrity that neutralizes anomalies automatically, much like your body's white blood cells. But just as importantly, the system needs physiology. This means accountability, auditability, and ethical controls are literally hard-coded right into the system's core behavior. Let's look at a concrete example. Say an AI suddenly starts making workload optimization decisions that would pull way too much power, risking an overload on a local community microgrid. The physiological governance automatically halts that action. It ensures the system physically cannot operate outside of its permitted, safe boundaries. Moving on to our final section, Section 5, Scaling Responsibility, the Implementation Transition. Transitioning to an AI-native infrastructure isn't just some one-time construction project. It is a continuous capability journey built across 4 key phases. First up is assessment, taking a brutally honest inventory of your power availability, data risks, and operational maturity. Second is the pilot phase. Now, the goal here isn't just to test the cool new technology, but to actively train your human organization. Remember, humans have never managed gigawatt-level intelligence factories before. So operational maturity is just as vital as the hardware. Third is scale, taking what works and turning it into repeatable architectural patterns. And finally, optimize, treating continuous improvement as your permanent operating state. The ultimate takeaway from everything we've looked at today is this: scaling intelligence inherently means scaling responsibility. As intelligence scales up and begins to directly touch real physical infrastructure, the margin for error drops to absolute zero. If we are engineering systems that will make autonomous decisions that impact major networks, energy grids, and everyday human lives, then those systems must have deep structural accountability embedded right within their physical and logical design from day one. As we transition deeper into this new era of engineered intelligence, we have to look at these massive, gigawatt-consuming factories and ask ourselves one absolutely crucial question. Are we building infrastructures worthy of the decisions they will increasingly support?